Hi students, in this video we're going to look at independence. Now after watching this video you should be able to define independence and also understand and recognize its relationship with conditional probability. You should be able to recognize independent events and also determine whether or not two events are independent or not. Alright, so the key things we'll have to recall are our formulas for calculating probability, and in particular our formula for conditional probability. So that is our probability of A given B is equal to our probability of our intersection of A and B over our probability of B, or put another way, the number of items in A and B out of the number of items in B. It's the same formula, just another way of expressing it. Alright, now let's consider the following Venn diagram. We've got P and H, two separate events. Now, the probability of P is pretty straightforward. We've got 10 out of 20, or 1/2, or 0.5. Right. Now, what independence asks is, does the probability of P change if something else happens? Right, so does the probability of P change if, let's say, in this case, event H happens? Now, how are we going to work that out? We're just going to start off with using our conditional probability formula. So let's find the probability of P happening given H happens. Right, we've got, that's the probability or the number of, let's go with the number of in this case, hey? Number of times P and H occurs over the number of times H occurs. So number of times P and H occur, well that's this number in the middle, that's 4, out of H over lot, that's 15. And that is not the same as 0.5, that's not even close, right? So if it was half, it would be something like 7.5 out of 15. That would be the same as half, but when we don't equal that value. So what this is meaning is the probability of P is changing depending on whether or not H happens, right? So that's our conditional probability. If these events were independent, then the probability of P should not be affected by whether or not H happens. So independent events mean they have no link. They are not dependent on each other. And the probability of a situation or an event happening in one case, it's the same probability if there's some condition. And that's what we mean by independence. All right. Okay, so two events A and B are independent if the probability of A does not change depending on whether or not B happens. Now this means the probability of A is not dependent on B. Now what does this actually look like? So let's consider our formula for probability or conditional probability. So our probability of A happening if B happens as well, that's our probability of A and B happening over our probability of just B happening. And now if they're independent, then that probability, our conditional probability, should also equal just plain old P of A. Probability of A, sorry. A intersection B over probability of just B. Now, this only works if they are independent, right? So if these values are equal, then this rule will hold true. So rearranging that further, the probability of A intersection B will equal the probability of A times the probability of B. And so here we actually have two formulas that we can use to describe or prove probability. We have this first one. So that's just straight from our definition. The probability of A happening given B is just going to be the same as the probability of A happening at all, right? B has no effect on our probability of A. But this second formula can also be quite useful. So the probability of A and B happening for independent events only is equal to the probability of A times the probability of B. And so there's our rule. And we've also got our second rule. The probability of A given B equals the probability of A. Right, now these two formulas can both be used to prove independence. Right. Now, if the equation ends up being true, then the events are independent. And if the equation is not true, then the events are not independent. So let's actually see what that looks like in an example. So we've got 200 salmon, and we found that 120 of them were Eastern Australian salmon, and the others were Western Australian salmon. It was also found that 64 salmon were longer than 74 centimeters, and of that 64, only 45 were Eastern Australian salmon. So let's determine whether the size of the salmon depends on the type of salmon that we've got. So we're talking here about independence, and the giveaway in the question is this word here, whether or not the size of salmon depends. So that's our independence question. All right, so let's set up some variables. Let's say E means the fish is Eastern Australian salmon, and L meaning the fish is longer than 74 centimeters. So what we want to show is the probability of our fish being Eastern Australian, given it's longer than 74 centimeters, should be the same as the probability that it's just Eastern Australian to begin with. If this equation is true, then our events should be independent. So let's just work them out one at a time. So probability of Eastern Australian salmon, that's 120 out of 200. Cross off the zeros. And we can divide those both by 4. So that's 3/5. Okay, for the probability of having an Eastern Australian salmon. Now, our next one, the probability of our fish being Eastern Australian if it's longer than 74 centimeters. So that will be 45 out of 64. Now, looking at that, we can't actually simplify that fraction any further. So that means this fraction here and this fraction here we need to directly compare, and they're definitely not the same. So probability of E does not equal the probability of E given L. So therefore, the type of salmon is not independent of size. Now, what that means, just in layman's terms, is that if you've got an Eastern Australian salmon, the probability that it is quite a large fish or longer is different than the probability of getting a large fish for a Western Australian salmon. The size and the type of fish, they depend on each other. All right, so let's do some other examples of independent events. So let's say we are selecting objects when they're replaced. That's an example of an independent event. So consider a bag that has 3 red marbles and 4 blue. If you replace the marbles, there's always a chance of getting a red marble of 3 out of 7, because as soon as you pick up the marble, you put it back and you have the same bag you started with. So with replacement, those events are independent. Now, when there's no replacement, that means it's dependent. Right? That means it's dependent because the probability of picking a red marble with our second pick will change depending on whether or not we picked a red or a blue the first time. Right, so in the above situation, if a red was picked first, the probability of selecting a red marble with the second pick is 2 out of 6 or 1/3. But if we picked a blue first, the probability of picking a red marble out with the second pick is now 1/2. So the probability is changing depending on what was picked first. So not replacing items is a conditional event. Replacing items is an independent event. Alright, so after watching this video, you should be able to define independence and recognize its relationship with conditional probability, recognize independent events, and determine whether or not 2 events are independent or not.